Hi everyone. Today we're going to start on chapter 10, which is our first chapter on solving differential equation. But we're going to start on very simple stuff, mostly things that you probably remember learning from previous year. So for 10.1, we're going to start on something called directional field. But before we get to that, let's talk about some basic concept first, such as what is, technically speaking, a differential equation. So a differential equation is an equation that relates a function, usually an unknown function, with its derivatives. So therefore, it is a function and its derivative together being used into an equation, which is what the word differential kind of stand for derivative, of course. The solution to a differential equation is basically the unknown function the solution to a differential equation is a set of functions. So it could be more than one that satisfy maybe my mistake. This probably should circle with the functions. So it's a set of functions that satisfy the differential equation when the function and its derivatives are put into the equation. So essentially, kind of the same thing as what a regular equation would do. When you have a solution, what you do is you put the solution into the equation, and it will satisfy the equation and make the equation into a true statement. So here's the same exact concept, except that the only difference is we're not putting in a number, which is a solution, but instead we're putting in a function as a solution. Okay? Now, give you some example that illustrate what differential equation is, and also at the same time give you some terminology that describe them. So here a very simple example. One example will be following. Let's say we have this equation, y prime plus y equal to x. So this is what we call a first order differential equation. First order differential equation. So what does the word first order mean? Well, because it involves the first derivative of the unknown function. Now, then here is also something that students often get confused. So in this equation, what is the unknown function? So if you look at this equation, the unknown function in this equation is y. Then what is x? So the tricky part here is that the unknown function is y. In this case, the y is actually also referred to as the dependent variable in this equation. And then what is x? Well, x is actually the independent variable. of y. So because remember, the unknown function is y, which is the dependent variable. As we define a dependent variable, it's like the output of a function. But a function itself must require an input, and which in this case, x is our input. So therefore, when we present this unknown function should be y equal to some function of x. Now, as a matter of fact, we can totally see that because I just happen to know one of the solution to this equation. Important to understand that differential equation often have infinite solution to it. The reason why I have infinite solution because of what you learn in BC calculus. In BC calculus, you learn that when you have to integrate, it will create what we call an indefinite integral because of the constant of integration, the plus c. So here, because the process of solving this first order differential equation would probably require some kind of integration to undo the derivative y prime, therefore it will generate some kind of undetermined constant of integration. And therefore, with that constant can be any numbers, we most likely have what we call infinite solution. So just so happen that I know one solution to this equation is this. So I'm going to ask you to kind of show how that works. So I'm going to ask you to show that y equal to x minus 1 is a solution to y prime plus y equal to x. So notice that in this expression right here, the y serve as the dependent variable, which is the name of the function, while x is the independent variable that used to define y. So therefore, in almost every single differential equation, what you have to pay attention to is that there should be at least two variables involved. One of them is the unknown function, which is the dependent variable, and then there would be an independent variable that might or might not appear in the equation, depending on the equation itself. Okay, so in this case, I want you to show that y equal to x minus 1 will satisfy this equation. So how do I do that? Well, so the way to do that is, remember what I said. Solution to a differential equation is a function that when you plug in the function and its derivative, it satisfies the equation. So what I'm going to do is, I'm going to go ahead and try to find out what this is. So I'm going to define first, I know y is equal to x minus 1. And therefore, y prime would just equal to 1. The derivative of x minus 1 is just 1. So now what I'm going to do is try to see if I do take the left side of the equation, would that become the right side when I plug in y and y prime? So therefore, my equation is y prime plus y. So based on what I know, that will mean that's 1 plus x minus 1. That's y prime. That's y, and I will add them. And so that becomes 1 plus x minus 1. Notice the 1 cancel out and leave you with x. So therefore now my equation is indeed satisfied. It does give me the same equation as we started. Is x minus 1 the only solution to this differential equation? The answer is no. There are probably infinitely more, and that's what we eventually learn how to do. Now, show you a second example, just to illustrate. Okay, the second example we're following. How about this equation? Let's say y double prime plus y prime equal to 0. So this is often referred to as a second order differential equation. Why is this second order differential equation? Well, you guessed it, because it involved the second derivatives. That's why I call second order. As a matter of fact, the order of the differential equation would usually indicate the derivative or the highest derivative involved. In a sense, the order is kind of defined just like the degree of a polynomial. And we will explore the connection between a differential equation, a very simple basic differential equation, and its connection with a polynomial function. Okay, but what you need to understand is differential equation often have infinite solution, and also differential equation have a great variety of many different types, and each type requires different strategy to solve. And as a matter of fact, that's the reason why when we start talking about differential equation later on, you will see that we use a lot of different adjectives to describe the differential equation. And based on how we describe the differential equation, we will have different methods to solve it. So be mindful of that. So this is a second order differential equation. The second order simply indicates as second derivative. Now what I'm going to ask you to do is this. I'm going to ask you to go ahead and show. Notice that in this equation, you only see the dependent variable. You didn't see x. So in here, you assume x is the independent variable. But in some cases, it could be t. But for us, most likely, if we're using y as our dependent variable, as the unknown function of a differential equation, then we usually use x as the independent variable, because we would usually represent y prime as dy over dx, and y double prime as d squared y over d squared x. But t could also be used, and some other letter could also be used, depending on the problem. So once again, don't get too tied down with that. I'm going to actually go and show that y equal to e to the negative x is a solution to this equation. So to show that, it's pretty easy. Just like what we did before, we're going to start with y. And we'll find y prime. So y prime, don't forget chain rule involved. That will become negative e to negative x. And then y double prime will be a derivative of y prime, which actually make it back into positive e to negative x. And so now what I'm going to do is try to plug in the differential equation and see if it actually come out to be what's on the other side. So I'm going to take y double prime plus y prime, so therefore equal to e to negative x plus y prime, which is negative e to negative x. And that come out to be e to negative x minus e to negative x. And that, both of them cancel out. That does give you 0. So therefore, it shows that it does equal to, does satisfy the differential equation. Okay? Now, for a differential equation that might have something that you have to plug in on both sides, you might want to show the equation in a slightly different way. In this case, you might want to kind of show that it satisfies the equation by showing that the left side and the right side are the same. So in this two example, you can simply just plug everything on the left side and then just show that it's simplified to what the right side is. But for this one, so let's say here's another example. Let's say ask you to do this, show that y equal to tangent x is a solution to the differential equation y prime equal to 1 plus y squared. So this one a little different because I actually put y on the other side. Now, as a matter of fact, very interesting to point out, when you have a differential equation, you actually would like to have them in what we call standard form, something worth writing down. So if you're not writing it down, you should. What is a standard form of a differential equation is when you collect all the unknown variable, unknown function, and their derivative, and put them all together on one side of the equation, while everything else on the other side. Meaning, in this case, this equation, written the way it is not in what we like to refer to as standard form. Okay? But if I rewrite it into this, then now it is considered to be in somewhat a standard form. Or later on, we'll actually talk about what form is called. But that would actually make the problem easier to check in some way. Okay, so now the question comes down to, like, how do I show that it will satisfy the equation? So I could definitely check it either this way, using the first expression, or the second one. If I do it in the second one, where I already put it into somewhat in a standard form, I can just plug in y prime and y and then square it and see if it come out to be 1. So that will work. But if I do it on this one, where y and y prime are on alternate side, then I'm going to have to do it kind of in a left right side and make sure they're equal kind of thing. So show you both of them so that you can see the differences between them. So actually, before I do that, how about I find y prime first? So y is tangent x, so therefore y prime must equal to secant square x. So now I'm going to kind of prove it both ways to show you the mechanics that are slightly different. So suppose I have y equal to 1 plus y squared. So the left-hand side would be y prime, which is equal to secant squared. What happened to the right-hand side? The right-hand side is 1 plus y squared, so become 1 plus tangent square x. And interesting thing to note is that tangent square x, 1 plus tangent square x, actually satisfy a Pythagorean identity. Now, if you don't know the Pythagorean identity, maybe we can do this. We'll just do some extra step on the left side to get it to work. Secant square x, technically speaking, is 1 over cosine square x. Now, what happened to 1 plus tangent square x? Well, 1 plus tangent square x technically is the same as 1 plus sine square x over cosine square x, because tangents is sine over cosine. And so what I'm going to do is combine that into one single fraction on this side, on the right hand side, so that becomes cosine square x plus sine square x. And I'm hoping that all of you recognize the Pythagorean identity now. Even if you don't know the two different variations, you should know cosine square x plus sine square x equal to 1. So therefore that becomes 1 over cosine square x. So now you can say that y prime is equal to 1 over cosine square x, which just so happen equal to 1 plus y squared. So therefore imply that y prime is equal to 1 plus y squared. That shows that the equation is satisfied. Now, if I put it into this form, which is y prime minus y squared equal to 1, then I can simply just go from left side and work my way to right side. So this requires slightly different methods. So let's see. So y prime is secant square x minus y squared would be tangent square x. Okay, oops, maybe I'll do this. I'll write out the same way we did. So therefore this would be equal to secant square x minus tangent x square. So that come out to be secant square x minus tangent square x. Okay, so I don't know what to do with this thing, so I'm going to go ahead and rewrite them both into cosine. So this is 1 over cosine square x minus sine square x over cosine square x. And then we'll combine these two things together, so become 1 minus sine square x over cosine square x. And some of you hopefully recognize that 1 minus sine square x is equal to cosine square x, but if you don't, notice that 1 can be rewritten using Pythagorean identity and say that this is the same thing as cosine square x plus sine square x, then minus sine square x over cosine square x. So these two things cancel out, leave you with cosine square x over cosine square x, which just so happen is 1. Therefore showing that 1 is equal to y prime minus y squared. So both of them show that the solution is, the tangent x is indeed the solution to the differential equation. Now, one last thing I want to talk about before we move on to the last thing I want to show you in 10.1. One video is all that is for 10.1. It's relatively short. The last thing I want to show you is this. Now, in chapter 3, notice that one of the most common words that we keep using in the entire chapter 3. And you can hopefully guess what word that is. And no, if you're thinking vector spaces, then that's pretty close. You're correct. It's kind of right. We do use the word vector spaces a lot in chapter 3, but that's actually another word that we use even more than vector spaces, because the problem is that we only introduced vector spaces in 3.2, and then we've been using it in 3.2 throughout the entire chapter. But something else we use in 3.1. So therefore, by definition, must use more than what we introduced in 3.2, and that is the word linear. Linear function is something that's very important in this course and in how we're going to solve differential equation. And the problem is the word linear is also going to be used to describe differential equations. As a matter of fact, the two differential equations that we just did in the beginning, this one right here, y prime plus y equal to x, and y double prime plus y prime equal to 0. Both of these two differential equations are referred to as linear differential equation. And the reason why they're linear differential equation, because the left side of both of these equations, where you're collecting all the y and the derivative of y together on one side, when you do that, you find out that on the left side is nothing more than linear combination of the unknown function y and its derivative. A linear combination of y and its derivative. Meaning that it involves only adding or subtracting multiple of either y or derivative of y. They're called linear differential equation. We'll talk more about it later on, but just since we're on here, I want to kind of introduce it so that it gives you more exposure when we talk more about it. And guess what? This equation that we're doing, y prime equal to 1 plus y squared, or in this form, y prime minus y squared equal to 1, is a non-linear differential equation. Why is it non-linear? Because of the y squared. Because of this y squared, the left-hand side no longer represents a linear combination of y and y prime. That's what messes it up. And when it's a non-linear differential equation, it becomes a lot more difficult to solve. And as a matter of fact, we'll focus mainly on differential equations that are linear for almost the entire course. We'll probably talk a little bit about some of the non-linear equation, but we're actually not going to go too deep into it because when you have non-linear differential equation, some of them are almost impossible to figure it out. All right? And I don't know about you, but I don't like things that are impossible to figure it out. So last thing I want to talk to you about is something that you probably remember learning back in BC Calculus. Direction field. So what is a direction field? One way to represent a differential equation is through graphically. Is to represent it graphically. So one way to represent a differential equation in the form of y prime equal to some function of x and y is to represent it graphically. As a direction field, or a name that's probably more familiar to you, or called a slope field. So the direction that you want to represent is actually represented by using a tiny little line that kind of give you the slope. So the reason why that is the case, because if you think about it, the equation y prime equal to f of xy basically assign the slope y prime to any given point xy based on how the function f define it. And so this association would allow us to graphically represent this into what we call a slope field by generating each point on the graph and showing what the slope is at that point. So in this way, using this assignment, oops, I missed an N. Using this assignment to assign a slope to a given point, you can basically use the assignment as a short line segment. So this assignment is usually represented graphically as a short line segment with the appropriate slope. Now, of course, just like what you probably remember learning back in BC Calculus, it's really hard for you to actually see what the slope is. And as a matter of fact, it's very difficult for anyone to draw the slope between like slope of 1 or 2 or 3 or 4 or 5 and on to infinity. So therefore, I'm not too crazy about what the actual slope is, but simply understand that horizontal slope must be a zero slope must correspond to a horizontal segment. A positive slope must be a segment that kind of point up to the right, and a negative slope must be point down to the right. And then you have vertical line that have undefined slope, and different positive slope would have a different like angle. And if you can do that, then I'm usually okay with your answer. So just be mindful of that. Now show you a very simple example just to illustrate this concept. So here's an example that some of you will remember doing in BC Calculus. Let's say sketch the direction field, or if you want to, you can call it slope field, of the differential equation. So when we present the differential equation, I must define the slope, or the derivative, equal to some function of x and y. So in this case, I'm going to say dy over dx, which is basically what our y prime is equal to negative x over y. So therefore, capital F of xy is this function right here, negative x over y, which allow me to plug in the x and the y value into this function, and will output a single number, where the single number represents the slope at that point. That's basically how it works. So show you how that is done. So remember, to generate a good slope field, it will probably require you to draw a lot of points. So I'm going to go and just ask you to do the following. How about we just do 25 points? So if you recall from BC Calculus, you're going to do a kind of table to kind of evaluate. But remember what I showed you in BC Calculus. When you form your table, remember to do the following. For the y, you will put 2 on top, 1, 0, negative 1, negative 2. You will not count from small number to big number on the y. The reason is because bigger numbers appear on top on the y-axis. So if you put negative 2, negative 1, 0, 1, 2, then when you draw your graph, you kind of have to flip-flop the numbers. So don't do that to yourself. Just organize them the way that it would appear on the graph. What do I mean by that? If you look at the table, there are 25 squares that you're supposed to identify 25 different numbers. Those 25 numbers would correspond to these 25 points directly. And if you use negative 2 on top and work your way down to positive 2 on the bottom, then you basically have to, basically meaning every top number on your table represent the bottom number on this graph. And that's just way too confusing. And trust me, I teach calculus. I know confusing. So now what are the number inside? So let's go and do this. So it should be pretty easy because you're just basically dividing the x by the y and then negate it. So negative 2 divided by 2 is negative 1. Negate it, become positive 1. Negative 2 divided by 1 is negative 2. Negative 2 negate is positive 2. Negative 2 divided by 0 does not exist. Negative 2 divided by negative 1 is positive 2. Negate it, become negative 2. And then take a wild guess what the last one is. Yes, it is negative 1. What happened to this one? Was negative 1 divided by 2, which is negative 1/2. Negate it would be 1/2. Negative 1 divided by 1 is negative 1. Negate is positive 1. Negative 1 divided by 0, that does not exist. Alright? And then guess what this one come out to be? Well, negative 1 and negative 1/2. Nice symmetry. Alright? And what happened to 0? Well, 0 divided by 2 is 0. 0 divided by 1 is also 0. This one is tricky because actually it wind up being 0 over 0. So I'm going to go ahead and call that does not exist. And then 0, 0. What happened to 1 divided by 2 is 1/2, negate is negative 1/2. Yes, it's not a surprise that this one would come out to be negative 1. It's 1 divided by 1 negate. And does not exist. As a matter of fact, this one also does not exist, so I'm going to go and do that. And then this one is actually positive 1 and positive 1/2. And take a wild guess is the last column without doing the math. You can probably guess that this will be because of that, because of symmetry. And yes, it is correct. That's exactly how it is. So now what would be the slope field going to look like? The slope field will look something like this. So these are 0. So I'm going to go and draw a horizontal line. And the one that does not exist, we actually interpret them as vertical line. And the next one I want to do are the ones. The ones are easy because 45 degrees. So positive 1 will be 45 degrees going up. And negative 1 would be 45 degrees going down. And then 1/2 would either be more horizontal than 1. But 2 would be more vertical than 1. There you go. So that's how the slope field look like. Several things that are interesting that I want to talk about, and that will be the last 2 things I want to talk to you about. Number 1 is that something called integral curve. An integral curve is a graphical solution to a differential equation represented by a slope field. So basically what does that mean is the following. If you think about it, all these line segments, short line segment, actually kind of represent what we call the tangent line. So if you basically look at the tangent line, you can kind of see how the graph look like. As a matter of fact, this particular slope field or direction field actually give you a solution that look like this. It actually gives out concentric circles that are the solution to the differential equation. And as you can see, this picture can represent almost infinite number of integral curve. As a matter of fact, I just drew 3 of them. And now the last thing I want to point out is the following, is if we can identify a specific integral curve as the solution to our differential equation, a specific integral curve as a solution to our differential equation, if we identify what we call an initial condition. If the integral curve must satisfy an initial condition. And the initial condition often represent as points on the curve that it must go through. And of course, in some cases, you could have multiple initial conditions. So it really depends on the differential equation itself. And you probably remember that problem where you have a differential equation and an initial condition is often referred to as an initial value problem. Okay, so we're going to run into those also. All right, unfortunately my time is up, and that is the end of 10.1. All right, so I'll talk to you again in next video. All right, bye-bye.